Imagine standing on a moon where the ground itself is trying to kill you, not through cold, though it is cold, but through fire. Lava lakes stretch to the horizon, their surfaces crusted over in patterns that split apart every few hours to reveal fresh molten rock beneath. Sulfur geysers blast 300 kilometers into the black sky, high enough that on Earth they'd reach space. The entire surface gets repaved by volcanic activity every few million years, erasing craters as fast as impacts can make them. This world has more active volcanoes than any world in the solar system, more than Earth, more than anywhere else ever observed. And here's the problem. This shouldn't be possible. The moon is small. Small worlds cool quickly. There's no radioactive core hot enough to drive this, no internal furnace that could explain what's happening. By every reasonable expectation, this world should be frozen solid, dead and cratered like so many other moons. But it isn't. How can a tiny moon with no heat source be the most volcanically active body humanity has ever found? The answer comes down to one fact about how gravity works across distance. Gravity pulls harder on the near side of an object than the far side. This seems obvious when stated. Closer things feel stronger attraction, but the consequences are anything but obvious. When a moon orbits a massive planet, the side facing the planet gets pulled more strongly than the side facing away. This stretches the moon along the line connecting it to its planet. If the orbit were perfectly circular, this stretching would be constant. The moon would bulge slightly, and nothing much would happen. But if the orbit is even slightly elliptical, the stretching varies. Closer in, the gravitational difference is larger. Farther out, it's smaller. The moon gets squeezed and released every single orbit, and this cyclic flexing generates heat through friction inside the rock itself. Think of bending a metal paperclip back and forth. After a few cycles, the metal gets warm at the bend point. The same principle operates inside a moon, except the moon is being bent by gravity billions of times over millions of years. This is tidal heating, and this single mechanism explains everything that follows. The moon in question is Io, the innermost of Jupiter's large moons. When Voyager 1 approached in March 1979, scientists expected to find a dead world pocked with ancient craters. What they found instead redefined planetary science. The surface looked like a pizza, orange, yellow, red, white, with no craters visible at all. A young scientist named Linda Morabito was processing navigation images when she noticed something strange, a bright crescent shape extending beyond Io's edge. At first, she thought it was another moon behind Io, or perhaps an image defect. But the geometry didn't work. The shape was attached to Io itself. She had accidentally discovered the first active volcanic eruption ever observed beyond Earth, a plume of sulfur and sulfur dioxide blasting 160 kilometers above the surface, visible only because it caught sunlight against the blackness of space. But here's what makes this discovery extraordinary. Just 3 days before Voyager's closest approach, a physicist named Stan Peale and 2 colleagues published a paper predicting exactly what Morabito would find. They had reasoned from pure physics. Io orbits Jupiter in a gravitational dance with 2 other moons, Europa and Ganymede. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This resonance, a gravitational synchronization, prevents Io's orbit from circularizing. Every time Io tries to settle into a circular path, the periodic tugs from Europa and Ganymede pull it back into an ellipse, and an elliptical orbit means variable tidal stretching. Peale calculated that the internal friction should generate more heat per area than any other body in the solar system. He predicted Io would be volcanically active before anyone had seen the evidence. The prediction appeared in Science 3 days before the confirmation arrived from 500 million kilometers away. The volcanoes on Io don't look like Earth's volcanoes. There are no shield volcanoes or stratovolcanoes building up over millions of years. Instead, lava lakes sit in calderas that can be 200 kilometers across, their surfaces constantly overturning. Fountains of lava spray hundreds of meters high. The sulfur compounds give everything that sickly yellow-orange color, while silicate lavas hotter than anything on Earth's surface today, hotter than 2,000 degrees, flow in rivers that can stretch hundreds of kilometers. Standing on Io would mean standing in a radiation bath from Jupiter's magnetic field, while watching the ground slowly but constantly reshape itself. The tidal heating is so intense that Io is essentially turning itself inside out. Remember, gravity pulls harder on the near side than the far side, and cyclic stretching generates heat. The same principle operating on Io operates on its neighbor, but with a completely different outcome. Europa is the next moon out, also locked in that same orbital resonance. It feels tidal heating too, but less intensely because it's farther from Jupiter and the gravitational gradient is weaker. On Io, this heat creates volcanoes. On Europa, it does something potentially more significant. It maintains a liquid water ocean beneath a shell of ice. The evidence accumulated slowly. Europa's surface is remarkably smooth, covered in ice with almost no impact craters. Like Io, the surface is young, constantly being resurfaced, but not by lava, by ice. Cracks crisscross the entire moon in patterns that only make sense if the ice shell is floating on something liquid, shifting and fracturing as the moon flexes. In some regions, the ice appears to have broken into rafts that drifted apart and refroze in new positions, like ice flows in an Arctic sea. The Galileo spacecraft orbiting Jupiter in the late 1990s detected something even more telling: an induced magnetic field. Europa doesn't generate its own magnetic field, but Jupiter's powerful magnetosphere induces currents in the moon, currents that require a conducting fluid: salty water hiding under the ice. Current estimates suggest Europa contains more liquid water than all of Earth's oceans combined. And unlike the ice-covered lakes of Antarctica, this ocean is global, possibly 50 kilometers deep, in contact with a rocky seafloor. On Earth, wherever liquid water meets rock and energy, life finds a way. Hydrothermal vents on Earth's ocean floor support entire ecosystems independent of sunlight. If similar vents exist on Europa's seafloor, and tidal heating should provide the energy to drive them, then all the ingredients for life are present. Not because Europa orbits in some habitable zone at the right distance from the Sun, but because gravity's differential pull warms a tiny moon from within. The same physics, scaled differently, appears across the outer solar system. Saturn's moon Enceladus, only 500 kilometers across, jets plumes of water vapor and ice particles directly into space from cracks near its south pole. Cassini flew through these plumes and detected water, organic molecules, and evidence of hydrothermal activity. This moon, the size of Arizona, has a subsurface ocean maintained by tidal heating from its resonance with other Saturnian moons. The plumes feed Saturn's tenuous E-ring, a direct spray of ocean water visible through telescopes. Ganymede, the largest moon in the solar system, sits at the outer edge of the Jovian resonance chain. It receives even less tidal heating than Europa, but enough over billions of years to differentiate its interior into layers, possibly including a deep ocean sandwiched between ice shells. Even Titan, Saturn's largest moon, though primarily warmed by atmospheric greenhouse effects, may owe some internal activity to tidal forces. The pattern is consistent. Orbital resonances maintain eccentric orbits. Eccentric orbits create variable tidal stresses, and variable tidal stresses pump heat into moons that should otherwise be frozen dead. This single mechanism, gravity's differential pull creating internal friction, transforms our understanding of where habitable environments can exist. Return to Io for a moment. The most volcanic world in the solar system isn't near a star, it's warmed by a planet. The most promising candidate for extraterrestrial life in our solar system isn't Mars, it's a moon of Jupiter, warmed not by sunlight but by the constant gravitational kneading that follows from one simple fact: gravity falls off with distance, so the near side pulls harder than the far side. The implications extend far beyond our neighborhood. Any gas giant in the galaxy with moons in orbital resonance could host the same physics. The number of potentially habitable environments multiplies dramatically when moons count alongside planets. Astronomers hunting for biosignatures have traditionally focused on rocky planets in stellar habitable zones where liquid water can exist on surfaces. But tidal heating means liquid water can exist inside moons anywhere, far from any star, maintained by gravity alone. The search for life should include not just planets, but any satellite system where resonant orbits pump heat into small icy worlds. Somewhere in this galaxy, there are likely countless hidden oceans, each one warmed by the same physics that drives Io's volcanoes and keeps Europa liquid. Some of those oceans have existed for billions of years, providing stable environments where chemistry might have assembled itself into something that metabolizes, replicates, evolves. And all of it traces back to one fact about gravity that seems almost trivial until its consequences unfold. The near side feels a stronger pull than the far side. Everything else follows from that. If you enjoyed this, subscribe to the channel.